হচ্ছে তোর ঠিক আছে আমার স্পেসিফিক লোকেশন আছে কিছু ইনফরমেশন
দেখছেন করে দেবো।
হ্যাঁ তোর হার্ড ডিস্কের ভিতরে তো কী বলে একটা পয়েন্টার মতো থাকে
হার্ড ডিস্কের সাথে আমি একটা ইন্ডেক্স তৈরি করে এরকম একটা কিছু
আমার কাছে টোটাল সামারি করলে এরকম বিষয় মনে হয়েছে যে ধর একটা টাস্ক যাদের ধর জব, এই জব অ্যালোকেশনটা তৈরি করতেছে হলো মেমোরি, ঠিক আছে? আর একটা জব কমপ্লিট করার জন্য অনেকগুলো প্রসেস হয়, এই প্রসেসটা মেনটেন করতেছে হলো গিয়ে প্রসেস ম্যানেজার। মেমোরি অ্যালোকেশন আর প্রসেস ম্যানেজারের দুজনের কম্বাইন কাজ করার মাধ্যমে একটা টোটাল আউটপুট আসে, যেটাকে আমরা একটা সিঙ্গেল জব বলতে পারি। এখানে একটা ইয়ে ছিল, ওই এক্সাম্পল আসছিল এরকম, এই যে মেমোরি প্রত্যেকটা জব অ্যালোকেট করে রাখতেছেন র্যাম স্পেসের মধ্যে। এরপরে হচ্ছে যেমন মেমোরি এই প্রসেস ম্যানেজার যেটা আছে, প্রসেস ম্যানেজার হচ্ছে কন্ট্রোল প্রসেস সিপিইউ, যেটা সিপিইউ এখানে যে প্রসেস 1 প্রসেস 2 এই যেটা রেড হয়ে গেছে, তার মানে এই কাজটা ডান হয় না। এটা দেখবি যে যখন প্লে দেই এই কাজটা ড্রপ হয়ে যাবে, আর যেটা হইতেছে সেটা কমপ্লিট হয়ে উপরে যাবে। আর এটাই বলছে এখানে যে একটা জব কমপ্লিট করার জন্য অনেকগুলো ছোট ছোট প্রসেস কমপ্লিট করে আসতে হবে, যেটার প্রসেস ম্যানেজার মেনটেন করতেছে। আর টোটাল জবের যে অ্যালোকেশনটা সেটা র্যাম ইয়াটা কাজ করতেছে।
মানে এখানে তো জাস্ট
স্পেসিফিক ফাইল ম্যানেজারের কাজ।
একটা ওভারভিউ দিছে, মানে একটা ওভারভিউ দিছে, মানে হয়তো
আরো স্পেসিফিকেশন আছে,
আরো ডিটেইলসে গেলে হয়তো আরো কিছুটা ক্লিয়ার হওয়া যাবে না। তবে ও যেটা বোঝাতে যাচ্ছে আমার সেটা মনে হয়েছে যে হ্যাঁ অপারেটিং সিস্টেম হচ্ছে একটা কি একটা ম্যানেজার, ঠিক আছে, যে তো ফাইল ম্যানেজ করে,
মেমোরি ম্যানেজ করে,
মেমোরি ম্যানেজ করে,
ডিভাইস ম্যানেজ করে,
মেমোরি ম্যানেজ
মানে সবকিছু ম্যানেজ
ফাইল
করে।
ম্যানেজমেন্ট করে।
দ্যাট মিনস অ্যাকচুয়ালি মানে এই সব কিছু আমরা কিন্তু একটা টার্মে যদি বলি এটা হচ্ছে রিসোর্স। তো অপারেটিং সিস্টেম অন কাইন্ড অফ রিসোর্স লাগে, ঠিক আছে? আমার ফাইল, আমার মেমোরি, ঠিক আছে, আমার ডিভাইস সব কিছু কিন্তু আমার রিসোর্স। এটা অন কাইন্ড অফ রিসোর্স লাগে। ওর কাজ কি? রিসোর্স ম্যানেজ, ঠিক আছে? রিসোর্সের মধ্যে প্রসেসও
মেমোরি স্টোরেজ বা মেমোরি ম্যানেজার যেটা, ওইটা নিয়ে একটু শর্ট ব্রিফ আছে।
মেমোরি ম্যানেজমেন্ট।
Hello, my name is Sean, and in this tutorial we shall begin with the Memory Manager and look at 3 old schemes of memory management. Single user contiguous was the first scheme of memory management, and it wasn't very efficient in terms of performance. A single job reserved the entire memory space. This job would be processed, and then the memory was cleared, allowing the next job to be loaded. If the job size was larger than the space available in the RAM, it could simply not be executed. This scheme is considered impractical for today's modern operating systems, as it would be very slow to process all of the jobs on demand. But what if you wanted to store 2 or 3 jobs in the memory? This is when fixed partitions came along, allowing allocated partitions to contain more than a single job at one time. All of the partitions were stored in a partition memory table to keep track of partition usage. The sizes of these partitions were static, meaning they could not be changed unless the system was rebooted. So you could see how this would be a problem. A dynamic solution was necessary to avoid having to reboot the computer every time you wanted to process a job. A dynamic partition's available memory is still kept in contiguous blocks, but jobs are only given as much memory as they request when they are loading for the processing. This has proven a significant improvement over fixed partitions because memory is not wasting in the partition. Unfortunately, this is not a complete solution. Both fixed and dynamic partitions need some way to allocate jobs to the available partitions. There are 2 ways to do this. The first fit quite simply finds the first partition that has sufficient storage space, not taking into account how much memory could be wasted in the allocated partition. The best fit first looks for the smallest partition, resulting in more space for other jobs. resulting in slower performance but better efficiency. So, when a job has completed processing, it is then removed from memory, also known as deallocation. With a fixed partition, this is fine. It is simply cleared. But when using a dynamic partition, it gets more complex to free up memory as it tries to join together adjacent blocks. So, looking at these simple allocation schemes, we can see there are still problems. Each one required the memory manager to store the entire program in the main memory at contiguous locations. We need to find a way to avoid having to keep the whole program in memory to run, and the restriction of storing the programs contiguously. What if we could divide the jobs into separate, smaller chunks? We can. Virtual memory is the solution, and we shall look at the evolution of 4 memory allocation schemes. Let us start with paged memory allocation, allowing us to divide the job into equal-sized parts. The sections of a disk are known as sectors or blocks, and the sections of main memory are known as page frames. Before executing a program, the memory manager makes some preparations. First, it determines how many pages are in the program, and then it locates enough empty page frames in the main memory so that it can pass all the pages into them. The adjacent memory blocks do not have to be loaded in as adjacent memory blocks. They can be stored in any available page frame in the main memory. Now, this is a more efficient scheme, but it does come with complications. We need a way to keep track of all the page locations, which increases complexity in the operation. Through the use of 3 tables stored in the part of the main memory, we can keep an eye on locations of various jobs. The job table is a dynamic list that contains 2 values, the size of the job and the page map table location of that job. The page map table contains important information for each of the pages, the page number, and its corresponding page frame memory address. Finally, the memory map table has 1 entry for each page frame, listing both its location and a status informing whether it is in a busy or free state. Now that we have an understanding of page map allocation, we can now see how demand paging works. It's very similar to the previous concept, but the main difference is that pages are loaded on demand, meaning that pages are only brought into memory when they are actually needed. The page map table we looked at before increases with 3 more columns. 1 to determine if the page is already in memory, known as the status. The second to check if the page has been modified. And the third to check if the page has been referenced recently. How do we determine replacement of pages? By using a page replacement policy. First in, first out. Least recently used, least frequently used, and most recently used are replacement policies used to change pages based on a specific algorithm. These are all pretty self-explanatory and are crucial to the efficiency of the system. So we have looked at page map allocation and demand paging. But what else is there? Well, we have looked at separating the jobs into pages. What if we could break it down even further? We can. Segmented memory allocation splits the job into separate segments that reflect the nature and structure of the code. Usually, when you view a script, it is separated into individual functions or subroutines that can be called one at a time. You may have a function called add that makes a calculation of 2 numbers, and a function called divide. We can call these one after the other, and they will run in the chosen order. Now, take all of these functions and label them as segments. Instead of using a page map table, we now have a segment map table that makes a list of all of the varied sized segments that need to be put in the main memory to process. Now we move on to the final scheme. It is a mixture of segmented and demand paging memory allocation. It offers the logical benefits of the segmentation idea, as well as the physical benefits of paging. There is is no new logic involved, but there are some minor modifications to point out. It makes use of both the segment map table and page map table, plus additional information of authority to read, write, and execute a file. A major disadvantage of this is the overheads and complexity of adding in more tables to handle the load. Why is virtual memory a good thing? Well, let's say we currently have RAM that is fully occupied and has no time for jobs waiting to be slotted into it. Because we use segmentation and paging, we can exceed memory capacity by turning to the backup memory, the hard drive. And although it's a slower alternative, it can act as an extension to the RAM. We have come a long way in memory, but at an increased processing cost. The operating system can provide a more efficient service to allow the CPU, the central processing unit, to handle jobs with better time frames and effectiveness. This has been shown, and in the next step,